And we're right back where we left off on the last video. So we have different muscles for different functions. There are muscles of quiet breathing. So these are the muscles of inspiration, because expiration for quiet breathing is a passive process. We also have forced muscles of inspiration and forced muscles of expiration. The diaphragm is our inspiratory muscle. So the diaphragm functions in inspiration, for quiet inspiration. External intercostals are going to help the diaphragm. So they are synergistic muscles that help the diaphragm with inspiration. They help to increase the size of that thoracic cavity. The increased size allows the lungs to be able to inflate. Muscles of forced inspiration, we have some neck muscles like our sternocleidomastoid, our scalene muscles, our serratus muscles, our pectoral muscles, pectoral minor, all function in increasing the size of the thoracic cavity even further to help us to inspire even more. And then we have muscles of expiration. A lot of these are our abdominal muscles. So we have the external oblique, the internal, transverse thoracis. We should have the rectus abdominis should have been on there. I swear it should be on there. Oh, it's okay. I don't know why it doesn't show it on here. Sorry. External obliques help to force air out by pushing. The rectus abdominis also pushes to push that diaphragm upwards so that we can expire even more forcefully or effectively. And so breathing, I'm going to move this figure so that you can see that picture a lot better. So there you go. Breathing requires us to be able to increase the cavity of our lungs. That's the function, or that's what breathing does. Hold on one second. I'm back. I wanted to bring my lungs in. So I have my little lung activity that I can show you, okay? So to be able to breathe, we have to increase the size of the thoracic cavity because breathing is associated with pressures. And so if we decrease pressure, we can increase the ability to increase our lung size. Make sense? So when we breathe, we're going to move the thoracic cavity in 3 different dimensions. We're going to move it anterior-posteriorly. We're going to vertically move our lungs, or move our thoracic cavity and laterally, okay? Hello. There we go. And so I told you that breathing is all about pressure. So how many of you have taken chemistry? Hopefully you all have at some point, and you all remember those wonderful gas laws. We're going to talk about a few of those gas laws in this chapter because they have to deal, or they do deal with pressure and volume relationships of our lungs. So the first one is called Boyle's Law. And so Boyle's Law states that if you decrease pressure, or no, that's not true. If you increase volume, you decrease pressure. And if you decrease the volume, you increase the pressure. So look at this. Oh, no, let me first go through the picture, okay? Atmospheric pressure is about 760 millimeters of mercury. And so we need to decrease the pressure in our lungs so that it's lower than 760 millimeters of mercury so that we can pull air in. So think of A as the atmosphere and B as our lungs. when they both have the same pressure, airflow is going to basically stop. There'll be air going in and out at equilibrium, so we're not going to get any air. But if we increase our lung size, we decrease the pressure and air moves in. If we decrease the lung size, that increases the pressure in the lungs and air moves out down its pressure gradient. So now let me show you this. This is kind of fun, I think. This is mine. I haven't let anybody else use it, so you can think it's weird or whatever. I don't care. But I hate that. I'm trying to do it so that you can see it really well. There we go. Okay. So this is, and I'm going to, yeah, I'll do it this way. This is the lungs inside. So these two balloons are your lungs. And this is your diaphragm. So when the diaphragm goes down, when I pull the diaphragm down, so we increase the environment of the thoracic cavity, the lungs can inflate. If I decrease, they deflate. Okay, so watch what happens if I blow. So there's a tiny little hole. Can you see that little hole? I'm going to blow in that hole. Okay, and I have the lungs closed. They're not blowing up very well. But now I'm going to open the lungs a little, okay? So you see how they were able to blow up? Because I increased the thoracic cavity size, the fake thoracic cavity. This is like something I just got this year. It's my baby. I love her. Anyways, I'm going to set her down on the side, and then I'll move my face again so that you guys can read through the information as I talk through it. So atmospheric pressure, I just told you, was about 760 millimeters of mercury, and this is at sea level. So where we live, we're at sea level, and because of that, we need to, so atmospheric pressure doesn't really change unless we change in altitude. So if we go higher up in altitude, then the atmospheric pressure goes down. If we go lower in altitude, atmospheric pressure increases. But atmospheric pressure doesn't change if you stay at sea level. So when we breathe, the atmospheric pressure stays the same. Our lung volume is going to change. So alveolar volume is associated with intrapulmonary pressure. Intrapulmonary pressure is the pressure within our lungs. Alveolar volume is the volume of air that can move into the alveoli. And then we have intrapleural pressure, which is the pressure within the pleural membrane. So as our volume of our thoracic cavity changes, it causes pressure in our thoracic cavity to also change. If we increase the thoracic cavity size, we decrease the air, and then air from the atmosphere can move in because it's always going to move down its pressure gradient. So here we have inspiration. At rest, when we're not breathing, we're going to be at 760 millimeters of mercury inside the thoracic cavity and outside. But when we go to inspire, the diaphragm is going to move down, and so you can see it here. It contracts, it moves down, increasing that thoracic cavity size. And when that happens, atmospheric pressure, which never changes, becomes higher than intrapulmonary pressure. And so air moves in. We move back to we're back to where our atmospheric pressure and intrapulmonary pressure are equal, so air stops flowing. And at that point, we're going to relax the diaphragm. Diaphragm decreases in the thoracic cavity size, and we end up having a higher pressure in the thoracic cavity or in our pulmonary tissue, and air is going to flow out until we are again at equilibrium. So one question I always ask my class is the diaphragm a voluntary or an involuntary muscle? We do not think about breathing. We don't have to think about contracting our diaphragm. So is it considered voluntary, where we have control over it, or is it involuntary, where we have no control? The answer, since nobody's here to actually answer my question, I'll tell you the answer to this big secret. It's still a voluntary muscle. It's skeletal muscle, but it's under autonomic control. So there's no pacemaker cells that are telling it to contract and relax like the heart, but there are nerves, specifically the phrenic nerve innervates the diaphragm and allows the diaphragm to contract, sends signals for the diaphragm to contract, and then it relaxes, typically passively. So we have control, autonomic control of the diaphragm, but we also do have some conscious control. We are able to control our breathing. So when you're done running 5 miles or something and you're really tired and you're going, you can slow that breathing down. You can be like, just breathe slower. You also can hold your breath so that when you jump in a pool, air or water doesn't go down into your lungs. You can blow really hard, opening a balloon up. So we have control over our breathing, but we cannot control our breathing to the point where we're choosing to say, stop breathing so we die or something. You've all heard children throw temper tantrums, and they're kicking their feet and everything, and they start screaming, and then they stop breathing. They're not going to be able to do that until they die, because your body would actually pass out and you would start breathing. So where is the respiratory center? It's in the brainstem, and it's found within the medulla and the pons, but mainly the medulla is the main region that controls respiration. We have inspiratory and expiratory regions of the medulla. The pons also has respiratory center that stimulates the medulla. And so there's a lot of factors that will influence our breathing rate, either increasing or decreasing that breathing rate. I'll move that there, sorry. Okay, I'll move it back. I'm always moving my face all over the place, aren't I? I'm going to stop here because I'm at 13:35, and I think it would be good if I put this entire section in one video.